I'm JB Baker, Vice President of Marketing for ScaleFlux, and we're going to lead you through how databases can take advantage of computational storage. So first, just a very quick intro to ScaleFlux and computational storage, and then we'll dive right into the benefits of computational storage for databases, and then examples of how you can achieve those benefits. So ScaleFlux has been around since 2014. We're a leader in this emerging category of products called computational storage. We were the first out into production with a computational storage drive, and now have our second generation of computational storage drive out in production. We have consistently been winning awards for innovation and leadership in computational storage across different industry forums. And now computational storage, a newer term in the industry, has come out there, and we've got a definition that's been worked out with dozens of companies who have joined an industry group called Storage Networking Industry Association. There is a working group focused on computational storage. And we've come to a definition that the core of the definition focuses on offloading processing from the host CPU to other devices in the system, reducing data movement, which those architectures enable much more parallel computation and helps alleviate bottlenecks that have come into existence in the overall infrastructure. Now, a computational storage drive takes the features of an enterprise class PCIe SSD and adds to that some compute offload engines. So within the drive, we're going to do some direct compute on the data. Now, to illustrate how this benefits the system, in the traditional processor-driven architecture, what we saw is all the data has to pass up through the CPU. Maybe there are offload engines with FPGAs on add-in cards, but all the data has to pass back and forth through the CPU structure. And that was fine when you had hard drives serving up megabytes per second of data. But as we've transitioned to SATA SSDs and SAS SSDs and now NVMe SSDs that deliver 3 gigabytes per second of throughput, and you put multiple drives in a system, now we've created all these bottlenecks up at the CPU. And there's very little parallelism in the compute function. With computational storage, what we do is enable a much more data-driven architecture where we move some of those compute offload functions. Rather than having them sit off to the side of the CPU, we put them right down into the drives. And what that is going to do is create a much more balanced overall structure. And it enables the compute to scale nicely with the storage performance, because every single drive bay is now also has some compute function in it. So we've got tremendous parallelism, and we're able to significantly reduce the overall movement of data and get rid of those bottlenecks. Now, for Percona customers, what the key focus is going to be around, okay, great, there's computational storage, but what does that mean for my database, right? What advantages can I realize there? Really two core categories of benefits. First one is going to be increasing performance, whether you're focused on queries per second, transactions per second, your latency or quality of service. We're able to improve those by alleviating those bottlenecks. And then secondly, if you're more DevOps or data center manager, reducing your cost. So cutting down the total infrastructure that's required to achieve a certain level of performance, cutting down the power that's needed, and reducing all those efficiency metrics like cost per query or cost per transaction or cost per gigabyte of data that you're storing. And we've done significant testing with MySQL, MariaDB, Postgres. All of these can see the benefits. Now, to realize the benefits, some of them you can do without making any changes. Some are going to require some minor tweaks to your database or storage engine, and others are going to be a little more innovative. So first, without code changes, we think about more transparent functions here, and we'll talk more in depth about the benefits of compression and decompression being offloaded into the drive. And then in the future, some encryption and decryption and additional features may be able to be added in. For the minor tweaks, what we're talking about here, some non-transparent functions, we're going to have to make some modification to existing storage engines or to an existing database. An example that we've deployed already is predicate filtering for MyRocks. And in the future, which Tong is going to dive into more details on these, some things like sparse logging and dual mode page format. And then more innovative side here may require even new data structures and an optimized storage engine where we're developing the software with the hardware, or the software to take full advantage of the new hardware capabilities. And Tong will go in more detail about these sparse data structures for key value. So first, with the transparent compression, we'll talk about the performance benefits. So this graph is pulled from the white paper that was produced by Percona testing our drives with MySQL. And here what we see in the dark gray is an ordinary NVMe drive running kind of baseline settings, right? And then we turned on host compression, and you see performance dip down to the light gray line when you use host compression with an ordinary NVMe drive. When you plug in the computational storage drive, which has built-in compression decompression, it boosts the performance significantly. So with double write buffer on, you can see in that light blue that we get to 2x the performance of the dark gray in many instances here. And the bottom of the x-axis here is the number of threads that are running. And then with the computational storage drive, we also do support atomic writes, which allows you to turn off the double write buffer to gain an additional performance boost shown in the darker blue. In terms of cost, utilizing compression can help reduce the amount of space that's consumed by your storage or by your database, right? And Tong actually early on, or 2015 here, and his students at Rensselaer Polytech had done a survey of industry data to see how compressible different types of data were. And they found that database data tended to be greater than 2-to-1 compressible, or cut from its original size by 50% or more. And then as we've deployed the computational storage drive with built-in compression decompression out to customers, they are validating the work that Tong and team had done and feeding back to us that they see 2.5, 3, 4, 5-to-1 compression with their database applications. So utilizing this compression could allow you to cut your storage footprint by 50 to 80%. Now, sure, you could use CPU compression to achieve a similar level of storage footprint savings, but that typically is going to come with a performance penalty. And we'll show that here. So in similar data, what we showed before, the dark gray here is the baseline of an ordinary NVMe drive running a 2.5 terabyte data set. Now we turn on host compression with that same data set, and performance dropped by up to 50%. And with this synthetic database, they achieved a 1.6-to-1 compression ratio using that host compression. What's happening here is you're burdening the CPU with performing that compression function instead of allowing it to focus on performing the database functions. Now with the CSD 2000, with the computational storage drive with built-in compression and decompression, well, we see we took a 4.7 terabyte data set. So this was much larger than the physical capacity of the drive, a 3.2 terabyte drive. And utilizing the compression, we expand the capacity. And what we see here is that while doing compression and storing twice the capacity, we achieve over 2x the performance of the NVMe with CPU compression. So we get the performance and the cost savings of the compression at the same time by utilizing a computational storage drive. So we talk about this as compression without compromise, or penalty-free compression, by offloading that compression function down into the drive and adding it with every single drive that you're putting into the system. And with that, I'm going to turn it over to Tong to lead you into more details about some of the minor tweaks.
Okay, yeah, thank you, JB. Okay, so yeah, the remainder of this talk will show that transparent compression could, beyond the straightforward deployment, the transparent compression could enable very exciting new innovation opportunities. Actually, it for the first time decouples the logical storage space utilization efficiency from the physical storage space utilization efficiency. In particular, as illustrated here, as this so in this cartoon, with transparent compression, actually we no longer have to fill each 4K byte sector with valid user data, and we no longer have to use all the LBAs. So as a result, the OS and the user applications can purposely underutilize the logical storage space in return for performance benefits, and meanwhile without sacrificing the true physical storage cost. So this really opens a very unique opportunities for system level innovations. So to better demonstrate the potential here, I will present a couple case studies under the 3 categories JB just mentioned. Okay, so under the first category of simple optimization without any code change, so let's look at Postgres, so the second most popular open source relational database. So Postgres, we know that it uses a parameter called the fill factor to control the amount of space reserved in each 8K byte page for future updates, which further determines a trade-off between the database performance and the storage cost. So that is like if we reduce the fill factor to leave more space for future updates in each 8K byte page, the database performance will improve, but meanwhile, the storage cost will accordingly increase. So as a result, Postgres actually by default sets the fill factor at 100%. So that means that to fully fill the whole page with valid user data. So in order to minimize the storage cost. Actually, interestingly, like once Postgres runs on the computational storage drive with built-in transparent compression, the storage overhead caused by the reserved space will largely disappear, because Postgres initialized the reserved space as all zeros, and the transparent compression can very highly compress those all zero segments. So this naturally enables Postgres more aggressively set the fill factor without sacrificing the physical storage cost. So to illustrate this, let the blue and the black dots represent the operating points when using our drive with built-in transparent compression as a normal NVMe drive. So with the default fill factor of 100%, they have pretty much the same performance, and our drive can reduce the physical storage cost by half through the built-in transparent compression. But once we reduce the fill factor to 50% under the normal NVMe drive, the storage cost directly almost doubles and the performance improves. So very clear trade-off between the performance and the storage cost. But under the computational storage drive with built-in transparent compression, we can expect the same performance gain, but meanwhile, the storage costs remain almost unchanged. So really if we further carried out the Sysbench TPCC benchmarking, we set the raw data set size at 1.4 terabyte. As we reduce the fill factor from 100 to 75%, from 100% to 75%, the TPS can improve at about 33%. But under the normal NVMe drive, the physical storage usage really jumps from 1.4 terabyte to 1.7 terabyte. But in comparison, as clearly shown here, that under our drive with built-in transparent compression, the physical storage usage only slightly increased from 340 gigabyte to 360 gigabyte. So this study clearly shows that by simply configuring the fill factor parameter, Postgres can take much better advantage of transparent compression to further improve the TPS without compromising the physical storage cost saving. Okay, so under the second category of minor tweaks on source code, now let's consider the implementation of a write-ahead logging. We know that in current practice, once we write one transaction into the in-memory log buffer and commit the transaction, the entire 4K byte block will be flashed from the buffer to one 4K byte sector on the storage. And after the transparent compression inside the computational storage drive, the compressed data block will be stored in the NAND flash memory. Then later on, once we write another transaction into the in-memory log buffer and then commit the transaction, the 4K byte block consisting of both current transaction and the previous transaction will be flashed to the same 4K byte sector on the storage drive and further compressed and stored to the NAND flash memory. So in the same way, upon committing the third transaction, we will rewrite the same 4K byte sector again and store the compressed data block. So clearly that as we keep flashing the same 4K byte sector to the storage drive upon continuous transaction commits, the exactly same transaction data are compressed and written to NAND flash memory again and again, really multiple times. So in this example, the same transaction 1 data are compressed and written to NAND flash memory by 3 times. So this clearly leads to the write amplification. So we know that a larger write amplification will cause more interference with normal I/O requests and of course, the shorter NAND flash memory lifetime. So clearly we want to mitigate this issue or even eliminate the write amplification caused by this write-ahead logging. So to achieve that goal, we can apply a sparse logging data structure. The basic idea actually is very simple. So instead of tightly accumulating data transactions in the write-ahead log, as in current practice, like for both MySQL, MariaDB, Postgres, always all the databases use the same way. And then instead of doing that, we always allocate a new 4K byte sector after each transaction commit. For example, after committing the first transaction, instead of appending the second transaction tightly after the first one, so we put the second transaction in a new 4K byte space and flash to a new 4K byte sector on a storage drive. So in the same way, for the third transaction, we put it in another new 4K byte space and to flash it to another new 4K byte sector on the storage drive. So by underutilizing the logical storage space of the write-ahead log, we eliminate the write amplification. And meanwhile, we still maintain the physical storage cost saving through the built-in transparent compression. So this clearly can help to improve the overall storage system I/O performance and meanwhile increase the NAND flash memory lifetime. Yeah, again, it's a very simple idea. So for the first purpose of illustration, this figure shows the physical write data volume normalized with the current practice. that here we assume that right after each transaction is committed to the write-head log buffer, we immediately commit and flash to the storage drive. Here, the horizontal axis is the size of each transaction, ranging from 128 bytes per transaction to 2 kilobyte per transaction. So the results here show that the smaller each transaction is, the more we can reduce the physical write volume. For example, like with 128 bytes per transaction, such a sparse write-head logging data structure can reduce the write amplification or can reduce the write volume by over 90%. Okay, so another possible like a minor tweak is to modify the relational database by deploying we call the dual in-memory versus on-storage page format. Again, the basic idea here is very simple. That is, when a page stays in a buffer pool, it keeps the existing conventional raw-based format. But when flashing a page from the memory to a storage, we convert it on the fly to a column-based format and transform each column to improve the data compressibility so that it can be better compressed by the computational storage drive. So raw and the column page format conversion is handled by the background IO thread in the database, completely transparent to other modules in the database. So for the purpose of demonstration, we incorporated this simple idea into MySQL storage engine, like InnoDB, by only adding like 600 lines of code. And our Sysbench-based benchmarking result show that the proposed dual mode page format can further reduce the MySQL storage cost by up to 50%. And the on-the-fly page format conversion only incurs very few percentage of TPS loss. So this simple idea can provide a very nice option for users to take better advantage of the computational storage drive with built-in transparent compression. Okay, so now let's talk about the last case study. So it is about the hash-based key value store. We know that in conventional practice, to implement hash-based key value store, we have to first hash the key space onto an in-memory hash table. Then the hash table further points to the location of all the key value pairs that are tightly packed on the logical storage space, which are further transparently compressed and stored into the NAND flash memory. So such an indirect addressing through the intermediate hash table can maximize the logical storage space utilization. But meanwhile, the memory footprint of the hash table is directly proportional to the number of KV pairs. So this leads to a very high memory cost for large scale hash-based key value store. So the very high memory cost is arguably the main reason why its real-world deployment of the hash-based key value store really pales in comparison to other key value stores with using other more memory efficient data structure like log structured merge tree. So leveraging the storage hardware with built-in transparent compression, we propose a so-called table-less hash-based key value store as shown here. That is, we directly hash the key space onto the logical storage space without going through a hash table. So by completely eliminating the use of a hash table, we remove the memory cost barrier on implementing the hash-based key value store. So meanwhile, by relieving the CPU from managing and searching the hash table, we can consume much less CPU cycles. So actually, as discussed earlier, that the indirect addressing through the in-memory hash table can guarantee compact placement of key value pairs on the logical storage space. But in contrast, the proposed table-less approach is subject to a significant underutilization of the logical storage space. That is, almost all the pages have a noticeable amount of empty space left unoccupied. But once we fill the unoccupied space with a highly compressible dummy data like all zero, we can still achieve almost the same physical storage cost as the current practice. So in summary, that by intentionally underutilizing the logical storage space, the proposed table-less hash-based key value store can completely eliminate the in-memory hash table without sacrificing the physical storage cost. So for the purpose of demonstration, we have implemented a prototype called the CalXDB and compared it with RocksDB using the YCSB workload. This figure shows compares the average throughput between RocksDB with three different compression settings and our CalXDB. The result show that the CalXDB consistently achieves higher or much higher operational throughput. For example, in the case of workload YCSBF with 50% of read and 50% of read modified write, CalXDB can achieve 2.5 times higher throughput. And meanwhile, the higher throughput comes hand in hand with lower read latency, as shown in these two figures in terms of average read latency and the 99 percentile tail read latency. And finally, this figure compares the CPU utilization in terms of CPU cycles per PV store operation. The results show that the CalXDB consistently consumes 2 to 3 times less CPU cycles when we're achieving the much higher performance. Okay, so in conclusion, that today we talk about how database could benefit from the new growing family of computational storage drive and presented several case studies to show the potential. So at ScaleFlux, we really sincerely look forward to working with the community to further explore how we could take full advantage of such a new storage hardware. So this ends our talk. Yeah, thank you very much.